All right, so before we get going, I got that next connect or the final connect and the final Excel assignment up there. We might just kind of touch on how you do that Excel assignment. To be honest, it's probably a little bit easier, should be a little bit quicker than some of the previous ones. I think they'll be more clear after today and Friday's class, kind of why. Once again, I dropped the lowest, so kind of if you don't do one, that'll be the one that gets dropped. Other than that, any questions before we jump into things here today? All right, so we left off kind of thinking about how do we find this line of best fit, right? So the idea behind what we're doing with linear, that's not gonna work. The idea behind what we're doing with linear regression is, we have all these data points and we're trying to draw a line that best fits the data. Whatever that line is, it's going to have some intercept A and some slope B, right? So we said, we could write this kind of as a general line. Our Y variable is a function of our X variable, right? As X goes up, Y will change by whatever that value of our slope is, right? So we kind of said the interpretation of this slope is for every 1 unit increase in X, our slope is how much Y increases by, right? You can kind of prove this to yourself, right? If you had like Y is equal to 5 plus 10X, if X is equal to 1, Y would be what? 5 plus 10 times 1, so 15. If X is equal to 2, goes up by 1 unit, Y would be, well, 5 plus, 25, right? As X goes up by 1 unit, Y is going up by 10, right? So that's a general idea behind what we're doing. And we're going to try to choose, we're not like in practice going to draw this line of best fit and figure out what the intercept and slope are, but we're going to let Excel kind of minimize the sum of our squared errors, right? So we said we want to minimize the errors that we're making. This line is like the average relationship between X and Y. We're going to be a little bit off, right? From every observation, we've got an error term, right? So we said we want to minimize the total amount of errors we're making across every observation, so the sum of the errors. But we're really going to square them because we don't care which direction we're off by, right? So squaring them makes a negative times a negative, positive times a positive, both positive. And it over penalizes really bad errors, right? So that's essentially what we're going to do. We would take a derivative in respect to A, take a derivative in respect to B, set them equal to 0. 2 equations, 2 unknowns, you can solve, right? However, the math isn't super easy. What we kind of end up with is a formula that looks something like this, right? So, I mean, this isn't too terrible. Like, you can kind of envision how we could do this in Excel. Here, we just got the average of our X and our Y variable, and don't feel like I can write this down. I'm not going to make you guys do this. I'm just showing you this for the sake of, I'm kind of setting this up. So we've got the average of both variables. I can go through every observation. If I had a column of data, I can just create another column where I take that X value minus the mean. That'd be fairly easy, right? Have the means in some cell, reference it, freeze it. Do the same thing for the Y variable. Then set up another column where I take that difference of the X variable from its mean, multiply that by the difference of the Y variable from its mean. And then kind of a similar thing here, just square it. So, and then, maybe a calculator friendly version, you can kind of rearrange things mathematically. But ultimately, it doesn't matter. I'm not going to make you do any of this computation because this would take us forever, right? What I want you to know is once we have these intercept and slope values, how do we interpret them so how do we interpret them when we get them from Excel, right? So I'll show you how you do them in Excel somewhat a little bit later today. I'll skip through this because I'm not going to make you do this, but, let's just use Excel, right? It makes our life a lot easier, and that's what we're going to do in practice anyways. So what we're going to need to do linear regression in Excel is follow the following steps, right? If you have a Mac, I think steps 1 and 2 might be going up to your toolbar, right? And then kind of going down to options, add-ins. But it's, you know, you'll click file, you'll go up, I think I believe it's tools or something on the top toolbar. Okay. So I will show you how it's open. Well, I put this data up on Canvas earlier. Let's do, I don't think we'll get to work through it completely today, but we'll at least introduce the idea. Okay. So I've got this GPA omitted variable. Let's just go to sheet 1. Here's where kind of the raw data was, right? So I had this huge data set. I've got a bunch of different college students. I have what their GPA was, SAT score, a 1-0 variable for whether or not they were a student athlete, et cetera, et cetera, et cetera. All right. So let's say, just starting out, naive regression, and I'd like to complete this today. I don't know if we will, but we'll see that the results can kind of change. So maybe I just am interested in, can I predict college GPA from somebody's SAT score? Right? So I'm going to go to File, Options, and then Add-ins. Like I said, on a Mac, I believe you go up to your like Tools at the top, and then there should be kind of an options there, and then you'll see add-ins. It'll look a little bit different. So in fact, we could probably just Google this and show you a good image. Oh. No, this is going to be the exact same thing that I just had. Yeah, so you go to Tools, Excel add-ins if you're on a Mac. Once you get to that add-ins, here's what I think on a Mac will be a little bit easier. But here on a PC, you'll have to go down to Manage Excel add-ins, hit Go. You'll want to make sure this analysis tool pack is selected. Okay. So once again, on a Mac, you should go to the Tools, right? Then go down to Manage add-ins or Excel add-ins. You should have this option of making sure this analysis tool pack is kind of selected. Okay. You find that okay on the Mac? Some of you guys find it? Okay, a couple hundred. Okay, just making sure. So we'll hit OK. What we now see is, if my computer stops being slow, there we go. If you go to the Data tab, you'll now have on the right-hand side this Data Analysis option. Okay, this data analysis has a bunch of built-in tools. We're not going to worry about any of them. In fact, some of them has like stuff we've done. Like there's some like 2 sample stuff, but it's a little bit different because it's an F test. We haven't talked about that. You've got some correlations, but we're going to want to use the regression tool. All right, so go all the way down to that regression. Whoops. If I can, there we go, regression. Hit OK. Now I can't zoom in on this, so I apologize, but you've got these 2 boxes, right? So one is you want to select your Y variable. The next one is you want to select your X variable. Remember last class I said some other terms. Our left-hand side, our Y, or our dependent variable, it depends on X. X is our X variable, right-hand side variable, independent. It's independently changing. So I want to try to predict college GPAs, right? So I'll select that college GPA. So my Y variable is going to be that GPA variable. So Control Shift, Command Shift on a Mac, hit the down arrow. I'm then going to go over, select that. I want to then select my X variable. So I got to scroll all the way up so I can show you. We'll select our X variable, which is the SAT score. Control Shift, Command Shift on a Mac, hit the down arrow. Hit this. Now, one thing we'll need to make sure, I think if I hit OK, I'm going to get an error here. It says I've got non-numeric data. Oh, well, it's because I selected the names of the variables. Now, it won't be quite clear why this is so important until we kind of go to the multivariate regression. But you'll always want to select the labels and then just make sure that you let Excel know, oh yeah, I selected the labels. Right? So the nice thing about this is once we get the output from Excel, it'll kind of have the names of those variables for us. So moving forward, if we have multiple variables, we can kind of identify which one is which. Okay. So I'm then going to hit OK, and you can change things. Like you can put it in the same worksheet and like select the range where you want it. You can create an entirely new file. I generally just kind of use the default where I create a new worksheet that has the results. So I hit OK. I'm then going to see it creates this new sheet. We'll zoom in so we can kind of see what we're doing here. I'm going to make this column wider just so we can see some of the names. And all of this we're not going to talk about for right now. All we need to focus on is what's down here. Okay. So we haven't even talked about test statistic or p-values related to linear regression, so we're going to hold off on that. All we're interested in is these what we call coefficients. Right? So coefficient is just a fancy name for the fact that when we estimate what these A and B values are from the data, they're just estimates, right? They came from some sample data. There is some true intercept and true slope we can't see, just like there's some true population mean that we usually can't see, right? So these are like sample statistics. So we'll call that the intercept coefficient and the slope coefficient, right? So here, intercept coefficient, slope coefficient on our SAT score variable, right? So it doesn't say slope, but it's the slope that's associated with whatever X group, there it is, X variable that you included, right, or that you used. So we've got here, right? This is essentially the effect of a 1 point increase, right? If that coefficient is our slope, that should be interpreted as the effect of a 1 point increase in our X variable, how much it predicts our Y variable changes by. In this case, goes up because it's positive. So what would a 1 unit increase in our SAT score be? Just one additional point, right? If I had like income as my independent variable, a 1 unit increase would be one additional dollar. If I had, I don't know, height on my right-hand side, 1 unit increase, 1 additional inch, right? So it's just whatever the units that X variable is in. So one more point on the SAT would predict that your GPA goes up by 0.002-ish, if I'm rounding it, which seems pretty small, but I mean, GPA is measured from 0 to 4, so we're not going to have a huge, huge movement. Also, it's 1 point on the SAT, right? The SAT, I've read the new one, right? This is the old SAT that was 1,600 points. So, we think about 1 point is not that much, right? But one thing that's kind of interesting I can do, if I know the impact of 1 point, how could I get the impact of, say, 100 more points? This is a linear relationship, and I know the effect of 1 more point. What's the effect of 100 more points? Just multiply, yeah, whatever that effect of 1 unit was, the slope, just multiply it by however many unit increase I'm interested in. Here I want 100 additional units. So just take that slope, multiply it by 100, right? We're just scaling that effect. Right? I don't think it's too crazy idea. If I know, that, if I, let's say, I don't know, that for every additional year of education I have, I make an additional $5,000. Well, then if I get 10 additional years of education, that would equate to $50,000 additional dollars, right? I'm just scaling that effect of 1 unit change up to whatever I'm interested in. So here, right, if I score 100 points higher on the SAT, that would predict my GPA is going to be about 0.2 higher. Well, that seems pretty reasonable, right? I mean, SATs aren't perfect predictors, but they should give me some information about the intellectual or underlying, like, academic ability of an individual, right? Any questions on that before we keep moving? So I don't have this written out, but it's going to be a good thing to write down. This will always be how we interpret our slope coefficients. We can think about it as a 1 unit change in our X variable causes the predicted Y value to change by whatever that slope coefficient we see for B is. Okay. So 1 unit change in our X variable will cause the predicted Y variable to go up by whatever that coefficient is, right? Whatever that value is. In this case, 1 more point in the SAT score would predict our predicted GPA goes up by 0.00193. Questions on that before we keep moving? Okay. So we'll come back to this here in a second. No, I went all the way from the beginning. I did not mean to do that. What do we want? We want, there we go. So we got that add-in, right? That data analysis we can use. I had this data that I found, well, actually, I had it laying around. There's this huge survey of individuals, and it had kind of their reported income as well as the number of days they, I said smoke here, I think it was used as marijuana every month. Now these are like younger individuals, so that's why you see pretty low incomes here. I think it was like 14 to 19. So like these are, a lot of this isn't necessarily, what we think of as like long-term career jobs, but right, they had their income that they were making currently, and then the number of days they use marijuana, right? So I kind of had this idea of like, oh, it'd be kind of fun to like run this regression where I try to predict income from someone's drug usage, right? So the number of days they use marijuana each month, and then what's the impact of that on their income? And don't worry about this, I was just kind of singling out 1 year, right? So I run this regression, and here I wanted to show you, we can do this in Excel. We can also do this in a lot of other data packages, right? So anybody heard of the program R? Yeah, a couple people. So this isn't R, but you can use R to run regressions. There's also a program called Stata, which is what this is coming from, right? So you can use a bunch of different, there's SAS, there's a bunch of different things you can run regressions in. I'll only expect you guys to know how to do it in Excel, right? This is kind of the most basic and easiest way to do it. But it gives us all the same thing, right? Now, one thing to point out here is it doesn't call it the intercept, it calls it the constant. It's just two different names for the same thing, right? I mean, in this regression, regardless of what X is, the intercept is always constant. So that's sometimes why we kind of use those terms interchangeably, right? So this is essentially my intercept estimate or coefficient. And here is my slope coefficient on the impact that the number of days someone uses marijuana each month will have on my Y variable of income. Right? So here, how would I interpret this coefficient? So what's a 1 unit increase in my X variable? It's measuring the number of days you use marijuana each month. A 1 unit increase would be, using marijuana one more day, right? Or consuming it one more day, however you want to kind of, verb you want to use that, right? So using marijuana one more day every month would predict that someone's income goes down by $253. So that's kind of how I would interpret that coefficient estimate. Any questions on that before we keep moving? Now, just a little bit of foreshadowing. We can interpret these coefficients, but what's probably true about someone's income is that, maybe their marijuana usage factors in and helps me predict it, but there's a lot of other things that are probably better predictors, right? So we're doing very naive regressions initially. We'll kind of eventually get to where we see, oh, well, I can actually control for a lot of other factors, right? But for right now, we're just kind of focusing on having one variable on that right-hand side. Okay? So if it seems a little iffy, it is, right? We're eventually going to get to where it makes a little more sense. One thing I want to mention here is, so we've got these coefficients or these estimates, right? So just like we had with sample means and unknown population means, if we have sample coefficients, right? Sample slopes, it's not coefficients or sample slopes. We don't know what the true slope is. We can do things like hypothesis testing, or you'll even notice some of the other output it gives you is confidence intervals. Now, we're not going to focus on the confidence intervals. We can kind of think about our test statistic. All we're going to do is take whatever that slope coefficient Excel tells us and divide it by something called this standard error. So you can kind of think about this standard error. It's really like the variance of that coefficient, right? It's just a kind of a fancier name. It's slightly different, but it's really just picking up the variation that exists in that slope estimate. Just like the variance that we had before picks up the variance we had in our original data that we calculated our sample mean from. This is calculating the variance within the data that we calculated our slope estimate or our slope coefficient from. So, and technically, if we're following kind of the traditional kind of how we calculate test statistics, we take our estimate for the variable, our estimate for the statistic we're interested in. We then subtract, and here we kind of write this goofy, but it's gamma 0. It's just, this is the predicted value of our slope coefficient. So to make this a little bit easier, you can kind of think about this as, what are we assuming that relationship is between our x and our y variable, right? And then we'll divide it by the variance of that, statistic we're interested in. Now here, once again, just like with the two population stuff, we're always going to assume this is 0. Okay, so this makes this a lot easier, right? Because then all I have is just take that coefficient divided by the standard error. So you can kind of see here, right? Negative 253 divided by 48, you get about negative 5. Right? That's all we're doing to calculate that test statistic. Once we have that test statistic, we can then look it up in our student t-distribution, find the p-value, right? So I'm not going to make you do this by hand. It's a little more complicated with our degrees of freedom when we do regression. But Excel or all these other programs will do that for us. Excel or all those other programs will do that for us, right? It tells us the p-value. Here, the p-value is pretty much 0, right? So we can definitely do what? If I have a p-value that's less than alpha, I can reject the null. What the hell is the null? Right? We haven't talked about it yet, right? So the null, I told you here, we're assuming that the slope is 0. When we do linear regression, what we're always interested in, we're not doing this to like find no relationship. We're always interested in, is that slope something other than 0, right? Is marijuana usage impacting income? Is our SAT scores, impacting predicted GPAs? So we always start out kind of pessimistically assuming there is no relationship between the two variables we're looking at. That's always what we assume. Now it gets a little double negative-y and kind of tough when we think about this. Here, if I can reject the null, I reject that there's no relationship, right? So if I'm rejecting that there's no relationship, what I'm really saying is I found evidence there is a relationship here, right? So it gets kind of tricky, but it's just because sometimes the way we speak doesn't line up with mathematics, right? We have to assume that there's no relationship here, that slope is 0, right? If we can reject that, we're saying the slope is not 0, or we found evidence that it is not 0. What we're really saying is we can reject that there's no relationship, or we found strong evidence that there is a relationship. Okay. Is that making sense? Any questions on this idea so far? All right, so we kind of already talked about this. We didn't talk about A. So we talked about how we interpret that slope coefficient. What about our intercept? I've kind of been ignoring that, right? So our intercept coefficient, if we go back here, what were the values? So here, if I wanted to start predicting income, well, first of all, I need to give myself a little bit more room. Where's my group? Got what? Negative 253. What was my intercept? 32,449. And that was going to be how I could come up with my predicted income, right? Remember, when we're making these predictions, this is like y hat, right? We're just predicting y. There are actual y values. That was the idea that this line, we're plugging in x and coming up with predicted y values, but the actual data, right? The actual y values might vary a little bit from that point. Okay? So how can I interpret my intercept? Well, my intercept, the way we're going to interpret it, and we'll end up having some pretty goofy interpretations down the road, but it's if our x variable is equal to 0, our intercept tells us the predicted value of our y variable, right? Because if our x variable is 0, 0 times any coefficient is 0, we're just left with the intercept or the constant. So the interpretation of our constant or intercept will always be if the x variable is equal to 0, the intercept is our predicted y value, right? So in this case, Given that someone uses marijuana 0 days a month, their predicted starting income here would be about $32,000 or $32,449. Any questions up to this point? So here I'll show you another one that is kind of goofy. So if we go back, so I can't remember these values. Let's say I was trying to predict GPA from SAT scores. So I get what? 0.66. So 0.66 plus what? 0.0019 was it? Yeah. So how would I interpret this intercept? So I just said the intercept will always be if that x variable is equal to 0, right? So this one, if somebody gets a 0 on the SAT, their predicted GPA would be 0.66. You get a 0 on the SAT, I would think in reality, you probably get a 0 GPA. But you know, this is the idea. Like, there is some starting point. And the reason why this one is goofy is because if we think about what we're actually looking at in the data, there's going to be some variables. So SAT is my X variable, GPA is my Y variable. Let me think how I want to set this up. So, right, like I don't think anybody's getting, I don't even know. I haven't looked at the data in a while. Can't imagine there's like anything below like 5, or maybe there is. But right, like there's some point where we don't see people getting 1 or 200s on the SAT. So all the data is over here, right? But if I draw a line of best fit, it has to hit my y-axis somewhere, right? It's just that in reality, I don't see any data points down here. But I would still interpret the intercept the same way. If I did see that x variable be equal to 0, here's kind of where my predicted y variable starts out, okay? That kind of makes sense why we might have maybe some goofy interpretations there if we just have a variable where we don't really see those values close to 0 actually in the data, right? But that doesn't mean the line doesn't have a start point. The line still has to have a point where it starts out at. All right, so we've already talked about this. And like I said, I'm not going to write it using this fancy gamma. We can just kind of always think about it. We're assuming the slope is equal to 0. We can do one-tailed tests. It's very like you could probably take every statistics course in the business school and you would never talk about doing one-tailed tests with linear regression. It's just very, very seldom that it's used. So for the sake of what we're doing, we're just always going to be using this two-tailed test, assuming that the slope coefficient is equal to 0. That's always what we're going to be doing. Okay. You know, and it would work exactly the same. Once again, I'm not going to make you do these steps, right? Excel does all this for us. Excel calculates that test statistic. I know, sorry, I shouldn't say I'm not going to make you do this. I might have you use Excel's output to calculate test statistics, but in practice, right, you actually just usually, Excel spits those out at you as well, right? I'm not going to make you look up the p-values. Excel will always kind of spit those out at us as well, okay? The only reason why I might ask you to do a test statistic on the exam is because it's like, hopefully, really easy points, right? I mean, if I've got Excel output, hopefully it's a very easy point to know, oh, my test statistic is just the slope coefficient divided by the standard error, by this number, by this number. I'm trying to give you some kind of easy questions if I'm asking you to calculate a test statistic, okay? Finding the p-value is a little bit harder. So I'm just going to rely on, you can use that p-value to make a rejection decision. Is that p-value less than alpha? If it is, I can reject that there's no relationship, right? Or that assumed true value for the slope of 0. All right. So we've already talked about this. Just to kind of give an idea, we're not gonna really use this moving forward. But what this standard error represents, I kind of already mentioned, it's like the variance in that relationship or that slope between x and y. So really what it's kind of measuring is the difference between our predicted y values and our actual y values. Squaring those differences, similar to a variance, right? We square the deviation from the mean. Here, we're squaring the deviation from the predicted y value. basically squaring the deviation from this line of best fit. Right. So we don't do this in practice. Excel does this behind the scenes, but our standard error is kind of giving us some idea about the variation that exists from the actual data and our predicted values. Okay. So, hopefully, let's see here. Well, we'll use this today. I wasn't sure if I'd use it or not. Hopefully this is an easy one if we've kind of been following along. But, oops. There you go. So let's say I have this other regression where I'm trying to predict the birth weights. Yeah, birth weights from whether or not a mother smokes. Right? So hopefully this is an easy one. I give you this output from Excel, right? It gives you the intercept coefficient and it tells you that slope coefficient. Right? Excuse me. If all I want you to calculate is the test statistic, hopefully that shouldn't be too bad. So I'll give you a little bit of time to work on that. You think we talked about this, it should be pretty easy to go pretty quick. You've got that slope coefficient. Also got your standard errors. If you didn't have that test statistic from Excel, hopefully you could be able to reproduce it pretty easily based off what we've talked about. Right. So most of us got our answer in here. For a second. All right. If you haven't gotten your answer in, take your best guess here. Okay. All right. Close it out. So I can just kind of eyeball this one. I mean, I'll have to put that mental math. If I look at this coefficient and standard error, what's my test statistic I'm pretty close to? If I do some egregious rounding, negative 200 divided by 50 is about negative 4. If I'm guessing, probably negative 4.3 there, right? All we're doing is taking that test statistic and dividing it by the standard error, right? So hopefully these are like really easy questions, easy points in the exam. That's all you have to do. I already said this, right? Just take your coefficient divided by that standard error, okay? Any questions on that before we keep moving? Okay. So I said this is a little hokey, right? In that, like, how am I just predicting like income from one variable? It doesn't make a whole lot of sense, right? Well, it doesn't. You're right, right? So, or I'm right. I guess I was the one that said it. But you know, what we want to do is try to control for a bunch of other factors, right? Maybe I want to control for age, right? What career field the person was in, all these other things. Okay. Now before we go there, I also did want to make one more point from this last example. Sometimes we can run regressions with 1, 0 variables. So here, whether or not the mother smoked while pregnant, this smoking variable is just a 1 or a 0. So here the interpretation gets a little bit different. So because usually we said the interpretation of our slope coefficient is a 1 unit change in x. But if my x variable is a 0, 1, what's a 1 unit change? Well, there it would just be going from the 0 group to the 1 group. So in this case, going from not smoking while pregnant to smoking while pregnant reduces birth weight by about 200 grams, right? Now giving us some indicator that it's not good to smoke while you're pregnant, right? It's bad for the child. Okay. So here, if you have a 1, 0 x variable, the 1 unit change is just going from that 0 to the 1 group, right? So we want to include more independent variables so we can try to control for other factors. So maybe it looked like smoking while pregnant was really bad for birth weights there. But what's probably true about, and you can maybe make some, well, if I was assuming what is some characteristics about mothers that smoke while pregnant, my guess is that it's coming from lower income levels, right? Lower socioeconomic classes. They might not have as great availability to, if I have less money, I don't have as good healthcare, or availability to afford healthcare. I don't have as much money to afford high quality food, maybe prenatal vitamins. So even though it looks like smoking while pregnant is really bad for birth weights, maybe it's just picking up the effect of all these other things that are correlated with smoking while pregnant, right? And they're all negative, right? Not having good access to high quality food, healthcare, what was the other one I said? Prenatal vitamins, things like that, right? So I want to be able to control for those factors. I want to be able to control for, well, what is that person's income? Then I could say, if I've got all these additional, if I include income on my right-hand side, so I start to include more variables. Now when I interpret my slope coefficient, it's still interpreted the same exact way. So if I think about my maternal smoking variable, let's say I wanted to predict birth weights. And I've got that smoking variable, but now I'm also including on that right-hand side my independent variable. I've now got 2 independent variables, right? I'm predicting birth weights now using multiple factors or multiple different variables. So now the interpretation of this coefficient on smoking while pregnant is it's the impact of a 1 unit change going from that 0 to the 1 group. So smoking while pregnant instead of not. Would predict that birth weights go down by -200, holding constant everything else that I've included in the regression. That's a lot more powerful of a statement, right? So here it's like holding constant someone's income. Now, what is the impact of going from not smoking to smoking while pregnant? And that's, pretty powerful. I can include not just one, I can include tons of controls. I can include mother's age. I can include, mother's education level, all these other things. Then the interpretation becomes holding everything else constant. So 2 mothers with the same income, 2 mothers who are the same age, 2 mothers who have the same education level. But one of them goes from the 0 to the 1 group. One of them smokes while pregnant. Now what is the predicted change in the birth weight? Right? That's a lot more powerful of a statement. Okay? So we can include several other variables on that right-hand side to kind of control for other factors that we think might matter. Right? Any questions on that idea? Is that makes sense here? And the mathematics behind it just gets like, I'll come back to this, right? You would still do the same thing, but I now take a derivative in respect to every single slope coefficient that I'm choosing. Now I've got more equations, it's the math becomes complicated. I think I put, someone else's is the next level class, where you would talk about this. We're not going to worry about it, but the proof is on that link. What I do want to highlight though is another example where we can think about why this might matter, right? And we won't get there. We won't get there in Excel today, but I've got a pretty cool example that we'll kind of start out with on Friday that'll kind of set up this idea that we call kind of this omitted variable bias. Okay? So think about if I'm got this regression where I'm trying to predict crime rates, and I wrote the slope coefficients a little bit different here because when we look at some of the output, or if you look at, if you read through the book or you look at other regressions, sometimes instead of calling these A and B, they just use beta to represent these. So beta 0 would always be the intercept. Beta 1 is the slope coefficient on your first variable. Beta 2 is the slope coefficient on your second variable. Beta 3 would be the coefficient on your third, et cetera, right? So let's say that I've got this police variable, which measures the amount of money spent on your police force, right? So I think this was like county level data. You can figure out how much is that county spending on their police force and what's the crime rate in that county. Or you could do this by city as well. Right? So if I just run this naive regression and I end up finding that this is, or sorry, I want to prove my point here. Let's say I find that the slope coefficient is positive. And I don't know, just to give it some context. First of all, if this is measured in the dollars that I'm spending on my police force, what do you think is probably true about the sign of that slope coefficient? Remember, how would I interpret that? What would a 1 unit increase be? If this is measuring the amount of money spent on your police force. $1 additional. So what do you think the impact of $1 additional on your police force is on crime rates? Really small, right? Now that's okay, right? Because I know the effect of $1, I can scale that up to like 100,000 extra dollars, right? But I know this is probably going to be pretty small, right? Just based off of how my X variable is measured. But if I find that it's positive, right, that would mean that if I spend $1 more on my police force, the predicted crime rates actually go up, right? So why might that be the case? Well, if I have more police available, more police hours, more police, maybe they're just able to find more crime, right? Detect more crime. But also, you would think just innately having a higher police force is going to deter crime, right? So, and over time they're going to get people off the streets that are committing crimes, and so having more money on my police force, hopefully, I think I'm doing this to reduce crime rates. So why might I see there's a positive effect here? Well, what kind of areas are probably needing to spend more money on their police force? Areas that already have factors that lead to crime, right? Lower income areas, right? Inner city versus kind of rural usually. And so one thing that we might want to control for is, well, what are the socioeconomic or what are the economic conditions of this area, right? One of the things we know that really matters when it comes to crime rates is unemployment rates, right? When unemployment goes up, so does crime, right? And so maybe these areas that have high unemployment have to spend more money on their police force. So when I ran that naive regression, I was really picking up not just the impact of spending more money on my police force, but also unemployment, right? The effect of unemployment, which I know as unemployment goes up, I would expect to see crime rates go up as well. Now, if I can control for employment, what we will probably see, if I had the data on this, I've seen some other kind of papers do this, where as soon as I start to control for like these economic conditions, now the interpretation is holding the unemployment level of the area constant. Now the impact of an additional dollar spent on my police force looks like it's reducing crime, right? So it can completely switch your coefficient as you start including these additional independent or right-hand side variables. And that kind of makes sense, right? Like I'm just controlling for more factors, right? I think I kind of did an example of this earlier in the semester. I think I did. Did I show you guys the powerlifting data at one point? I think. So that's the same idea. I could run a regression where I'm trying to predict the amount of weight lifted and whether or not someone's male or female. Well, I'm going to end up always finding a positive effect there if I think about the variable being is the person a male, right? But if I start to control for things like height and weight, right? Now I start to see the effect of that male variable basically goes to zero, right? If I'm controlling for all these other factors, right? That's a lot more powerful of a statement. I'm actually picking up more of the exact relationship between the X and Y variable. If I don't include those factors, my results are going to be a little bit skewed, right? In an example like this, I might find the exact opposite sign of what that true relationship is. Okay. So 5 minutes here. Let me think what I want to do. We'll talk about R squared in the next class. We'll dive into this idea of correlation versus causation, including additional control variables and how that impacts things. Okay. So one of the variables that you'll see in your Excel regression output is this R squared. Okay. Now, R squared is always going to be in between 0 and 1. Okay. Now, what it represents is the proportion of the variation in our Y variable that we are explaining with all of our x, or all of our right-hand side, or all of our independent variables. So it's the amount of variation we can explain. So what do you think if you're trying to make predictions about something? What percent of the variation would you want to be able to explain? Ideally, 100%, right? I want to be able to explain all the variation. That way I know my predictions are capturing everything that matters. The lower that percentage gets, well, if I'm only explaining 5% of the variation, there's a lot of other variables I've omitted that probably matter, right? So my predictions aren't going to be as accurate. So this R squared is essentially the proportion. So it's not in terms of a percentage. It's kind of spit out of this as a proportion, but it's the proportion of that variation in our Y variable we're explaining with all of our X variables. So kind of the idea here is our numerator takes our predictions minus what the actual average is. This is kind of like how much variation there is in our predicted Y's. We're making these predictions for our Y variable based off the variables we included. We're then going to say, okay, how much variation is there in our predictions? How much variation is there in the actual Y values, right? The difference between the actual Y values and the average. We'll then kind of take the ratio of the two, and this is essentially telling us the proportion of variation our predictions explain relative to the proportion of variation in the actual data. Right? We want this to be as close to 100%, or in this case, if we're talking about proportions, we want our R squared to be as close to 1 as we can get, right? And if it's not, then we start to be a little bit kind of skeptical of our results, right? We can still interpret them the same way. We still can interpret slope and intercept coefficients the same way. But if I've got an R squared, it's like 0.16. I'm like, man, I'm explaining 16% of the variation. There's still a lot of other things I'm not capturing, right? So I might want to try to include not just not just SAT score. Maybe I want to start to include some of these other variables as well, right? As I add more of these variables in, what do you think probably happens to that R squared? Goes up, right? So we can actually see that play out. So we'll go to that data tab, data analysis, regression, hit OK. Now notice it always keeps in what you put in there last. Well, our Y variable is GPA, hasn't changed at all. My X variable now, I'm going to say, okay, I want to include what was their SAT score? Were they a student athlete or not? This verbal math test they made them take the high school rank, right? And I'll go over to the female variable. I'm just going to include some of these. Hold Control Shift, Command Shift on a Mac, hit the down arrow. It selects all of my independent variables there for me. I've got the labels selected. Now when I hit OK, I can see, sure enough, including these additional control variables, increase the proportion of that variation in Y I could explain, right? Went from 16 to about 25%, or 0.16 of the proportion to about 0.25 or 0.26. Okay. So you probably get started on that Excel assignment, running some of these simple regressions, doing some of the interpretation. We'll do a little bit more of the predictions and talk about kind of this omitted variable bias on Friday. Other than that, I want to mention before you guys get out of here, I'll put an announcement up on Canvas. I'm only going to be in my office from 3 to 4 today instead of 2 to 4. I'll add an additional office hour tomorrow. So tomorrow I'll be in my office from 2 to 5 instead of 2 to 4. Okay. I'll put an announcement up on Canvas as well. All right. I'll see you guys on Friday.